Okay, welcome back, Physics 20s. In this section, we're going to talk about motion. You're probably pretty familiar with motion, but we're going to look into a little bit more depth for what it is and how to calculate it. So first, again, you're familiar with motion. I'm sitting in this chair. If I said, am I moving? You'd probably be able to say, no, you're not moving. You're just stationary in a chair. But I want to consider this. What if we look outside of this room and we look at the Earth? I'm sitting on the Earth, and the Earth is actually moving very quickly. It's spinning like this. And if we step out even more and we look at this Earth, it's going around the sun, also very quickly spinning around in this direction. And if we look even further out and we look at the sun, it's actually moving in the Milky Way galaxy, which is a pretty fast speed. And we think, well, the Milky Way galaxy, that's got to be stationary, but actually that's moving as well. So when I ask the question, am I moving? It's kind of a difficult thing to answer. And what I want to conclude from this is that motion is relative to other objects. So right now, I'm not moving relative to the chair and to the Earth, but relative to the rest of the universe, yeah, the Earth is actually moving quite quickly. So in this lesson, we're going to have to consider sometimes moving relative to different things. But first, we're going to look at how to describe motion. We saw vectors and scalars from before, and we have a vector and scalar quantity for motion as well. For a scalar quantity, it's called speed, and we're going to determine it by dividing the distance traveled by the time it took to travel that distance. And for our vector, it's called velocity. This is one we're going to use more often, and it's the displacement over a certain amount of time. These both often have answers in meters per second, but velocity has to have our unit of meters per second and a direction. We'll also have kilometers per hour, but most commonly we'll have meters per second. So like we did with distance, I want to show some examples of distance, displacement, speed, and velocity, showing those four things that we're going to calculate. So first, we're just going to look in one dimension and say Amir walks 200 meters east in 50 seconds. What is the speed and velocity? So I'm going to draw an arrow going east, just like this. What's this distance, displacement, speed, and velocity? This is 200 meters. I'm going to start with the distance. He went 200 meters. This is a pretty easy example. The displacement from where he started to where he ends up is also 200 meters, but that's going to be east. Remember, I have to consider the direction for vectors. Now I'm going to put the speed. That's calculated by our distance divided by our time. So that's 200 meters divided by 50 seconds, and I'm getting an answer of 4 meters per second. And for velocity, it's going to be the displacement. Again, it's the same 200 meters divided by 50 seconds. And I get 4 meters per second, but I have to include the direction of east. And so in this example, the speed and the velocity are going to give us the same values. And we're going to get the same value for speed and velocity whenever it's traveling in only one direction. This is going to be coming up pretty regularly in the course when something's traveling in one direction. And I'm often going to be referencing velocity for those cases. Now, we can ask other questions based off these formulas. For example, how far will Amir go in 3 minutes? Okay, so I'm going to use the velocity here because he is going in a straight line. You could use either one because they're the same value. But how far is he going to go in 3 minutes? So the equation is V is equal to D over T. Most technically, I should put the triangle there to show that it's displacement, but I'm hoping you can just remember that D is going to stand for displacement. I might forget to put the triangle in a couple times, so hopefully you can remember that V is displacement over time. And this one is saying, how far does he go in 3 minutes? So we're asking for the displacement. To rearrange this, I'm going to times by T on both sides. Time multiplied by velocity will give me displacement. So 3 minutes, 3 min times our velocity of 4 meters per second. But we notice here that we have two different units. We have minutes and meters per second. If we want our answer in meters, we're going to need our time, that's seconds here, to be seconds here as well. So I'm going to change this into seconds by multiplying by 60 and go 180 seconds times 4 meters per second. And I'm going to get an answer of 720 meters. Okay, so actually pretty far, long way that he's going to go in that amount of time. Because I did do velocity, I have to include direction, which is going to be east. So they're not too hard. The equation V is equal to D over T is not that hard to rearrange. We showed some of this at the start of the course, but there will be some questions looking for velocity, displacement, and time. So that was for going in a straight line. I want to do one where we're going not always in a straight line. So if Amir walks 200 meters east and 100 meters west in 100 seconds, what is the speed and velocity? So now I'm going to show these going 200 meters east and then 100 meters west. All right. So our distance, if you went 200, then 100 is 300 meters. And our displacement for this case would be from where he starts to where he finishes, which is only 100 meters in the east direction. We saw this in the previous lesson. Now let's take that to speed and velocity. Well, speed is our distance, 300 meters, over our time of 100 seconds. And we would get 3 meters per second is his speed overall. But his velocity would be, well, his displacement of that 100 meters over that 100 seconds, and he gets 1 meter per second. So this is where we see that they're different, and I'll explain kind of like why they are. For covering that amount of distance, 300 meters, he was covering that at a rate of 3 meters per second, and most commonly, that's how we're used to saying how fast he's going. So what does the velocity mean? That kind of means to get from here to here, the average rate that he was progressing towards that was 1 meter per second, because really it isn't so efficient for him to go to here, take the path of going past it and coming back. So it doesn't really tell us like how fast he was going during that route. It says just from going from his start to his finish, what is his average pace to get there. And it is also important that we include the direction there. So I would have to put east in my answer as well. This isn't really used as commonly. Like for example, if you were here, you drove somewhere and you drove back and your speed was say like 200 kilometers per hour, but you came back to the same spot, your velocity would be your displacement, which is 0 over the time. So you would be going 0 kilometers per hour. And this is mostly what we focus on in society, how the speed that you are going. The cop's going to pull you over for going 200 kilometers per hour as a speed. If you say, well, I returned to where I started, so I was actually going 0, I don't think he's going to let you off. So that's kind of the difference between those two. But when they're in a straight line, they'll be the same. Next, we're going to look at simultaneous velocities. And this means when two velocities are happening at the same time. We're going to draw this with vector diagrams or arrows like we saw in the last lesson, except for they're going to be happening at the same time, not one after another. So we're still going to use angles and vectors and those arrow diagrams just like we were before, but now multiple velocities are going to be happening at the same time, not to say like we went here and then we went here, but there was two motions going on to produce a net result of moving in an overall direction. Again, this doesn't make a lot of sense when I'm saying it in the notes, but we'll do some examples. I just want to note this is different than displacement because the motion is in one direction. I'll kind of draw it out. That'll make a little more sense. So if we were to walk in this direction and then this direction, where we end up is going to be that far away along the hypotenuse of where we went. But we still walked this whole route that I'm kind of bolding here. What we're going to be talking about now is if you have two things contributing to your velocity. So say maybe you're flying a plane and you set it out in that direction. So you fly a little paper airplane or a remote control or something like that, but there's a wind going in that direction. Okay, we're going to draw a very similar diagram and say that the overall velocity is like that green arrow. But the difference is that the plane is going to follow that green area. That's where it's going to fly. It doesn't go forwards, then the wind blows it this way. It's traveling along this angled line. So that's the big difference between our previous vectors for position and now dealing with motion. But just like the other diagrams, our diagrams can be broken into parts and added together when we're looking at these arrows. To get a bit of a sense of this, let's think of those walkways, those moving walkways that you might see in an airport that look like this, where you can walk on them, but they're also like moving forward. This is how we can think of putting multiple velocities together. So let's consider this person is standing on a moving runway, or I think it's called a moving sidewalk. And let's say that it's moving in this direction at, let's say just 2.0 meters per second. If the person is walking in this direction as well, give them a green arrow, walking in that direction, maybe they're going at 2 meters per second as well, then their velocities are going to add together. Relative to someone who might just be like standing in the back here, they're going to see this person moving forward at 4 meters per second. So the 2 adds on to the 2 and we get a total of 4. So I would draw that with arrows like this. I would draw, he's moving at 2 and then I would switch to red, say the sidewalk is also moving at 2, and our overall, which is put just in orange here, would be a total of 4 meters per second. So they add together like that. Let's do another example where let's say that I'm going to put the sidewalk again in red. It's still going the same speed at 2.0 meters per second. Now the person decides to run in the other direction. Maybe that's fun for them. And they're going to run this way at 3.0 meters per second. What's their overall velocity going to be? Well, if I go to the red here, I have an arrow going this way, and then I have a green arrow going this way. This was 3, and this was 2. So then my overall, if I'm going to draw my orange, from where I kind of begin, the velocity ends up going this way at 1 meter per second. All right, so if someone here was standing on the side, they would see them moving at 1 meter per second in this direction. All right, so that kind of shows you how velocities can be added together in 1 dimension back and forth. But now we're going to look at velocity when it's in 2 dimensions. So let's say that we have a river here and we have a boat right there, and it wants to travel across the river. So it's aimed at the other shore and it's going to be driving in that direction. But at the same time or simultaneously, the river is flowing downstream at that angle. What that's going to do is that's going to produce an overall velocity of the boat traveling at this red arrow. So again, the difference, it's not going to go across the yellow and then pause there and get pushed up by blue. It's going to be moving along this line. That's the motion that we are going to see from the boat. Similar diagrams, but that's the difference in the motion compared to the position. So let's do an example of this. A boat is driving at 10 kilometers per hour east on a river, and the river is moving 4 kilometers per hour north. What is the boat's velocity relative to the shore? So I'm saying relative to a stationary shore. Sometimes people get tripped up on those words. What I mean is, like, if it's going at 10 kilometers per hour on the river, relative to the water, it's just going 10 kilometers per hour. But since the river is moving as well, if I'm comparing it to the shore, something that's not moving, I need to consider both of these velocities together. So that's what I mean by relative to the shore, relative to something stationary. So let's draw this out. He's going at 10 kilometers per hour east. So I'm going to draw an arrow like that. Let's make it a little easier to see with some blue. All right, so I'm going to put 10 kilometers per hour. But then the river is also moving 4 kilometers per hour north. So now I'm going to add on an arrow there of 4.0 kilometers per hour. All right, to figure out his velocity relative to the shore, I have to add them together, and I get that the boat would be traveling at this angle, and we need to figure out the speed of that. So really similar to the last calculations, I'll use Pythagorean theorem of 10 squared plus 4 squared square root, and I get an answer of 10.77 kilometers per hour. So that's his velocity, but because we are looking at velocity, we also need the angle of this. So to find this angle here, I'm going to use inverse tan, like we saw in previous lessons, of opposite 4 over 10 adjacent, and I get an angle of about 21.8. All right, so my answer here, I'm just going to round to 2 digits here. So I'm going to say 11 kilometers per hour at 22 degrees. And how am I going to describe that? I'm looking at this angle. This is directly east, and we are north from there. So north of east is our answer. So that's all we have for the lesson today. Make sure you ask some questions in the live time, try those practice questions, and I'll see you in the next video.